Hi everyone, I'm Jill Slansky. I'm a tumor immunologist. Can you hear me? Yeah. Okay. I'm a tumor immunologist, and so I'm going to give you a little bit of my story because the other Jill, which by the way, Jill's a good name, said that you guys like to hear a little bit of that. So I really liked biology, like from the very beginning. Like if a dragonfly hit the grill of the car, I like to pick it out and check it out. You know, like all all biology is pretty cool. And then I went to college, and most of you guys are there, and I loved biology, but then I started taking math, and I loved math. Like I like to lock myself in the closet and do differential equations. But I know that my dad said, "Oh, that's not going to last very long because it gets really weird soon." And I thought, okay, back to biology. Went to biology, and then I started going more molecular, and I loved that. Right, like you can find out how things work. And then when I got my first lab experiences, which maybe you guys. This isn't your first, but or maybe it is, and it was really awesome. You get to see how things work and work on them until they work, and the joy of the band. Have any of you had that yet? Where you like see a band on your gel? That was the best thing that. And so I'm very easily excited by finding out new things. And then I just kept going, and I said, okay, I'm going to keep going until I don't. And so I'm still doing science, and I'm still enjoying it. And when I finished graduate school, I went to a talk by a guy at the NIH who's like Papa Tumor Immunology. And he gave this talk where he was adding IL-2, which is a T-cell growth factor, to patients with cancer, and they were not very often, but they were sometimes coming back. Their cancers were being cured at a low rate, but I was like, I gotta have a piece of that because the immune system is a really cool thing, and if we could get the immune system and cancer to talk to each other, we're gonna have like real progress, and that's actually what's happening in the field. And so how many of you have had immunology? Okay, there's a few, yeah. So you guys know more immunology than you think, though. So that's what I want to just get a review of. Okay, so shout out so I can hear you. What do you know the immune system does?
Alerts the body.
It alerts the body, so it's like a warning of invasion.
Gets rid of anything it doesn't recognize.
Oh, sorry if I can't spell. So removes the foreign, right? Actually, that's similar. Removes foreign invaders. Sorry, I don't know how to spell foreign. What else? So the immune system talks among itself, right? So many. What's the science word for that? Sorry, let's talk really loud. Communications. So, can you think of anything else it does? Inflammation. So that's like, yes, there's many parts to that. Antibodies? Yeah. That can go in a lot of different categories, right? It can go in the next category, which we're going to talk about. What are some of the specific cell types, because the cell types make antibodies, but it's also something that contributes to inflammation. It's also something that neutralizes viruses. So antibodies are very central. What else?
Memory, when you see that again.
Isn't that nice, right? You can get a vaccine for the flu, and then you get memory from that vaccine, and you don't get the flu. That's like the best. Very convenient. Is there anything else? See, you guys know some immunology, right? It's going to all sound familiar. So what are some of the cell types that you know about?
T cells.
T cells. Yes.
Lymphocytes.
Max. Bees. I heard that. DCs. Good. Newts. Which one? Eosinophils. We're just going to call those EOs. You already know about my spelling. Basophils. Okay. See? Okay. So this shows you that you are going that this is very accessible field, even though it's an entirely new field, not new in general, but it's maybe if it's new to you right now, you know more about it than you think. Okay, so now I'm going to go to slideshow, and now your lists have made part of my talk. Okay, so in a broad sense, the immune system is a mechanism that allows a living organism to discriminate between self and foreign, right? Self or non-self. So early on, in the 60s and 70s, 50s and 60s probably, the immune surveillance hypothesis was proposed. And this hypothesis says that the immune system will recognize and destroy developing tumors by identifying foreign antigens on their surface. And these foreign antigens are generated during the transformation process. So you guys know about transformation. You know that to go from a normal cell to a transformed or a cancer cell, there's changes that happen. And so if the immune system can recognize those, then the tumor goes away. Okay, so there's one thing that goes along with this hypothesis. One corollary is that tumors will increase with immune suppression, right? And this actually is the case. So there was a huge study done in Pittsburgh where they took all of the transplant patients who are all on immune suppressives, right? So they don't eject somebody else's tumors. And those guys were, in general, at like a 25% higher risk of getting all sorts of cancers. Not just viral cancers, but epithelial cancers and cancers from different layers of development. So this is actually true. A small but significant number of tumors spontaneously regress. Which tumor do you think that they saw this in first? Say it super loud because I didn't hear that. What? A lymph node tumor? Yeah, because you would see it, right? Maybe if you have like a tumor in your lymph node, it would be a tumor and then it would go away. Or what about tumors on your skin, right? There's this story, plenty of stories where you're sitting behind somebody in class and they had a big melanoma or a big pigmented spot that then disappeared, right? And some people actually tried to quantitate this because it's more of a story versus that you could actually put a number on. And the number is about a fourth of a percent. So not something you want to count on, right? Okay, then another piece of evidence for the immune surveillance hypothesis is that when pathologists look at cancer under a microscope and they find lymphocytes, this correlates with a better prognosis. And this actually took a while to figure out because a lot of pathology has focused on the cancer itself, right? So they move around the slide until they find a piece that doesn't have a bunch of those pesky little lymphocytes in it, and then they look at that part of the tumor. But pathologists have actually known about tumor infiltrating lymphocytes for a very long time, so not a new thing. So this whole immune surveillance hypothesis has been updated, and it's been looked at in much more detail now that people are using immune therapies for cancer, and so this new model is called the immune editing model, and it's divided into 3 phases.
Can I ask a question before you?
Oh, yeah.
So, the immune system recognizes a cancer cell as cancer and not normal because it expresses maybe a mutated protein on its surface. And that mutated protein might be one that's typically inside the cell. Why do cells sometimes express these things on the outside?
Yes. So you're asking an antigen presentation question. So antigens get presented on the surface of all cells, and they present proteins that are found within the cell, and they can be normal proteins, they can be mutations from cancers, or they can be viral proteins. And then the T cells that are surveilling the body will be able to respond or not to that. Now, so if say you have a tumor that's got all sorts of mutations on the inside, and then it dies, and a dendritic cell, somebody knows about dendritic cells, I heard you earlier, swallows up the dying tumor and processes it and will put all of those potential mutations on the surface. So then a T cell comes by, gets activated, and then will go and find its prey. We have a video of that in a minute.
Okay, so it's a normal thing that cells do to say, look, I'm normal, I'm here, pass me by, and a cancer cell puts up a mutated version. Got it?
Yes. Yep. So it's happening all the time, and it's happening with our normal. We have cell death going on that's normal all the time, and a lot of things get presented that are totally normal, and we don't have responses to those. Okay, so back to the immune surveillance hypothesis. This includes more, and I'm sorry that the words are little. This includes 3 phases, and it's more than just the elimination phase, which is similar to the immune surveillance hypothesis that we just talked about. It includes all of these other cells, not just cells that recognize antigens like B and T cells, but all the other cells. See, you already know these cells: macrophages, neutrophils, dendritic cells, NK cells. All of these are involved. If you could think of this model over time, if the immune system doesn't get rid of the tumor cells, then the cells can actually enter an equilibrium phase. And immunologists think of it as an equilibrium phase. Tumor biology sometimes think of this as tumor dormancy, or it could be when you go into remission. I don't mean you. When somebody with cancer goes into remission. And this phase can last for a very long time, up to 20 years, right? You have or longer, right? Sometimes the tumor might get a little advantage, and then the immune system gets a little bit of an advantage. And so just so you know, there's going to be a talk about immune equilibrium today down at the King Symposium. I think Dennis Roop is going to talk about a really cool model that he used, that somebody in his lab developed. So just put that on your radar. And then escape phase. And escape is when the tumor wins, right? And notice elimination, equilibrium, and escape. They all start with an E. So somebody was excited about that. Okay, so this case, which I had audio for.
Case 1.
You can hear it.
A woman's treatment for melanoma was registered.
No, you can hear that, but that's not fair. Okay, so I'm gonna since it's not coming out of the speakers, I'm gonna just give you my with my voice, even though it's not as good as that other guy's voice. So this was in a case that was presented in the New England Journal, and this woman had melanoma, and she went and had it scooped out by the surgeons, and there were clean margins, which means there are no tumor cells that they could see that they left behind. And then she was followed in the melanoma clinic for 15 years, and then after 16 years, she died from something else. And she was an organ donor, so she gave her organs, she gave her kidneys to two different people. And this first woman who got her kidney went in for normal mammography, and they found a secondary melanoma in her breast. And it turned out that she died from metastatic melanoma that was from the original woman. Then the other kidney went to this guy, and he also got a lump in his kidney, and then he got rid of his immune suppression, and he rejected his kidney, and this guy, he survived. Okay, so isn't that crazy? It's a crazy story. Okay, so what happened? Why was the tumor detected in the kidney donor? Why wasn't the tumor detected in the kidney donor?
Is it an equilibrium for immune system?
Exactly. Perfect. They were living together, and it apparently everything was fine. So, why did melanoma grow in the recipients?
Immunosuppressed, so that the kidneys weren't rejected.
Right. So, what if they hadn't been immune suppressed?
Might have been fine.
Would they have been able to keep their kidneys, though? No, because the kidneys looked like a foreign thing. And so the immune system would not have liked that either. Okay.
Don't they match the kidneys?
So they can match. So you could get a perfect match, and that would be from your identical twin. But even the people. So when you go for a match, you get. They look at a number of your different HLA molecules, and you have 6 that are from class 1 and 6 that are from class 2, and they're very polymorphic. They're like the molecules that they match are the most polymorphic molecules that there are. And so you can say you're lucky and you find somebody who has 12 that are the same. All 12 of your HLA molecules are the same. There's still all the other differences and polymorphisms and allelic differences that are going to become an alarm bell to your immune system.
Why would someone who is in remission from cancer be able to donate such a vascular organ to someone? The likelihood of it metastasizing to your liver or your kidneys is so high. Why would she even be
nobody had any idea. So this is 2003, right? Which doesn't seem that long ago to me, but that's a long time ago for in biology years, right? So now, because of studies like this actually happened in this case. It happened with 13 different donors and 26 different kidneys, and so they have enough information now to make that against the rules. Okay.
Yeah, and in 2003, they thought she was cured of cancer.
Right. It didn't come up again for 16 years. There was no indication. And you know, that reminds me. So if the we go through trends in science, right? And some of them are kind of fun. So there's the one about we are always being peppered with cancer, right? But our immune system is in there taking care of us. And then that falls out of favor, and then another one comes back. Well, maybe we're not being peppered with all cancer, but think of how many people, it's probably like 95% of us have, by the time we die, have had HPV virus, or not HPV, the EBV virus. And EBV has some strong oncogenes in it, right? And so maybe our immune system is fighting off EBV-caused tumors all the time. You know, there's a lot of mental games. We'll never know, really. Well, that's going to be difficult to figure out. So, okay. So moving along. So we know, do you know about these guys? The hallmarks of cancer? So they, I met this guy when I was in grad school, and this guy kissed my hand when I was in grad school. I was pretty pleased. It was nice. So, these guys, Hanahan and Weinberg, have tried to write reviews that encompass all of cancer. You know, something that you can give to your parents and say, "Here, this is what I'm learning about this summer." And in their recent, which isn't really that recent anymore, 2011, they finally acknowledged that the immune system is part of cancer as well. Okay. So there's so much about this. Like, we could do the rest of the summer talking about this. And so what I did was I chose the two things that are the most successful and are being used the most in the clinic right now successfully. And so that when you guys go home, or when your auntie calls and says, "Hey, I heard about this thing on the newspaper," that you can say, "Yeah, I can talk to you about that. That's good." Okay, so the first one of these are called checkpoint blockade therapies. So I'm going to tell you about how they work. And the first part of this is our movie. This is a picture. This is a video of a T cell killing a target cell, and let's see if it works. Okay, so the little guy is the T cell, right? And he's mostly nucleus, and you can kind of see that. And he's poking. What's he giving, Dale? He's giving perforins and.
Come on, Dale.
Anyway, he's shooting all these vicious molecules at the tumor cell, and see how the tumor cell is starting to shrivel up? That is that's apoptosis. That's sort of a more programmed cell death, and we're finding that there's a lot of other kinds of cell death that can now be more immunogenic than this. But I was trying to get Dale to say perforin, granzymes and perforins. Granzyme, thank you, because that's what he's working on this summer. Okay. Oh, there it is again. Okay, well, maybe it doesn't want to do the next slide. Okay, so that was a T cell. Now we're going to take a look in cartoon world about how this actually takes place. So the T cell receptor from the T cell binds to the antigen on any other cell in the body, including tumor cells. And if it's an activated T cell, it will kill the target cell, just like we saw in the video. Okay, the T cell receptor recognizes MHC and HLA that we talked about, the same molecule, just H stands for human. M stands for major, not mouse, but you could think of it as mouse. There's MHC molecules on every cell. And so my question to you is, what protein do you think peptides presented from MHC molecules come from? Where do those peptides, where do the antigens come from? The cell? Are they going to be, what kind of proteins are they going to come from? So normal cellular proteins. I already said this, that's why it doesn't sound right. They're going to come from viruses, right? Pathogens. Why we're in this class? Cancers. Yeah. Okay. So there's that list. Okay. And then the other thing that we know about to learn about checkpoint molecules are about antibodies, which I know some of you are already tuned in with antibodies. So antibodies are made from B cells, and they can either be on the surface of B cells, or they can be secreted from B cells or from antibody-producing cells, and which are differentiated B cells, and can be in the serum. They're soluble. They can go throughout the entire body. And what are antibodies made from? They're made from a variable region that binds to an antigen, and this can be very good tight binding. And they're made from a constant region. And you can think about a B cell like a key, right? If you have a key, you have the variable region at the end, right? That can go into the lock. But that lock, that key isn't going to be very useful unless you have the part that you can turn, right? The functional part that happens. So you have your variable region and you have your functional part. And both of those are super important in these therapies that we're going to talk about, the checkpoint blockade therapies. Okay, now I know that this is got a lot of tiny words on it, but the main point is that this is between a T cell and any other cell in the body. Particularly, we call them antigen-presenting cells, which is any other cell in the body. And so more than just the peptide MHC molecule, the T cell can interact with a lot of other ligand receptor interactions, right? And the ones that are being targeted right now are called PD-1 and CTLA-4. And PD-1 sends negative signals into the T cell. And CTLA-4 can also send negative signals into the T cell. So if you turn on either of those receptors, the T cell becomes less useful at killing the tumor. So I have a few slides to make that a little bit clearer. Okay, so normal T cell activation takes place when the antigen-presenting cell presents peptide MHC and binds to the T cell receptor, and then you get a positive signal, and the T cell can then kill what it's interacting with, or can be set free to go kill something with that antigen on it. So other things that bind will then change this signal into a negative signal. So this is PD-1. PD-1 from the T cell binding to PD-L1, and PD-L1 is expressed on a lot of tumors, right? So the tumor has figured out a way to turn the T cell off. And then people, clever people, have figured out a way to block that interaction. So the blocking antibodies will just cut that off. They can no longer interact. The T cells can no longer be turned off. So what if instead we used an antibody that sends a signal through PD-1? Right, that can happen, right? There's antibodies, you select them in the lab for either positive or negative blocking or activating activity. So what happens if you turn on this pathway? It's going to inactivate the T cell, right? The T cell gets turned off even worse. So you've got to make sure you have blocking, not a stimulating antibody. Yeah.
Does it matter if you block PD-1 or like PD-L1, or do you get like the same effect?
That's a great question. So it's not exactly the same, but people are definitely using both. So if you block PD-L1, you don't get stimulation through PD-1. So that's, in that part, it's the same. But it seems that there's also some signaling that goes into the antigen-presenting cell that might also be included in that formula of how things are happening. Still under investigation. Yeah.
Does PD-1 have any other function for the T cell other than inactivating it?
I don't think so, but PD-1 is expressed on other cells besides T cells that are just now being identified, and there's also soluble PD-1 receptor found in places, so it's probably not as simple as it was initially. Yeah.
And what's an activating antibody? Should they all block?
Right, so what if, so sorry to go back to this horrible picture, but what if we made an activating antibody against CD28, right? Since we can do this in the classroom without having to try it on people, like it was actually tried on people. It was a big mistake. So, so if you made an activating antibody that turned on CD28, that is going to turn on the T cells, and you're going to have activated T cells across the board, whether you have peptide MHC interaction or not. And that actually ends up in a cytokine storm. And they tried this on 6 young men, went in probably just to make a little bit of extra money. So they thought, I'll be in a clinical trial. And they gave them anti-CD28 antibodies and had cytokine storms and ended up almost dying, like organ failure across the board. And then they went from being like, these 20-something-year-olds to over 6 hours aging and becoming this bad scene. And there was it happened actually. Why I heard about this while I was driving to give one of these classes, and so then I was like, oh, and guess what happens if you use a CD28? So yeah, good question. Okay, so there's not very many updated Kaplan-Meier curves to look at how anti-PD-1 or the many varieties of anti-PD-1 antibodies that are out there work, because everything is in such flux. But this shows 2 years of people with lung cancer who either got the therapy or did not get the therapy. And so there were a lot of people who lived, and now there's a lot of people who you could say are cured of their cancer. But then we've also found that some people are starting to just like with chemotherapies and with the other cancer therapies that are out there, are the cancer is evolving and is figuring out ways to work around the immune therapy. Okay, so we have another case here. This is an anti-PD-1 antibody case. Okay, a 90-year-old man was diagnosed in August 2015 with stage 4 melanoma, and this is not a good prognosis. Plus, he's 91 years old, and it was found in his liver and brain, so it had already metastasized. He was treated with surgery, radiation, and Pembro, which is an anti-PD-1 antibody, and he's still alive today. So my questions for you are, how might radiation help Pembro therapy? So is inflammation going to be a good thing? It totally could be a good thing. I think that there's still pieces of that to be figured out. Yeah.
Isn't it increasing like mutation rate in cancer, so it's presenting more antigens not recognized?
Exactly. So the T cells will come in because now there's all sorts of new antigens being presented, and T cells are being activated. So how might radiation hurt the whole situation? You could probably answer that question again with the same answer. But is there another one? What does radiation do?
The cells that you're trying to activate the T cells.
Very good. Exactly. So T cells are one of the most radiation sensitive cells that there are, right? So this can go both ways. Maybe the thing to do is to make it very targeted. And I think there's some people, and maybe some of you are working with them. I think there's some people on campus asking questions like that.
Maybe radiate first.
Radiate before giving the Pembro.
Yeah.
Yeah. And radiate away from large numbers of T cells. So secondary lymphoid organs, stuff like that.
They're probably, eager to get the immunotherapy on board. They don't just wait.
Right. There's that. There's all sorts of things that have to be considered. Okay. So so I got this, yes.
Since it had already metastasized in his brain, how can that anti-PD-1 antibody cross the blood-brain barrier?
Oh, that's a good question. So I think it can, but say it can't to figure this out. So if you have your T cells being activated in elsewhere, which is a whole other conversation again. But you have maybe those T cells then once they're activated can make it into the brain. Okay. So I think and it seems to have worked with this guy. Okay, so I got this case from the New York Times, and this is who it was.
Case 3. A 91-year-old male was
sorry.
diagnosed.
Okay. Do you know him?
Jimmy Carter.
Yay! Okay, good. All right. Jimmy. Yeah. So, he's still with us. Okay, so here's another one. This is sort of another important concept. So, a 66-year-old female without any personal or family history of diabetes was started on an anti-PD-1 therapy because she had this giant jaw tumor. And 7 weeks after starting the therapy, she had 3 doses of anti-PD-1. She ended up with something that looked like diabetes, type 1 diabetes. Brittle. Like she went from every day just, a regular jaw cancer patient to then being diabetic. So, my questions, again, are suggest how PD-1 antibody might have contributed to diabetes.
It allowed the
T cells deactivated, and maybe they were like hyperactivated just entirely, and so they started attacking her.
Yeah, her pancreas.
Yeah.
Right. So there's some of the cells that were being held at bay were specific for pancreatic antigens, and then they were set free by the PD-1 antibody, and then they attack the pancreas.
They have information about like what her like B cells look like after the treatment with PD-1. Like 'cause that, I mean, for like pancreatic B cells can be like the target for like to cause type 1 diabetes.
Right. So I don't think they did, because when this happened, they were a little bit shocked this could happen. But why were they shocked? Because we have anti-self T cells everywhere that are held at bay. Right. The whole selection process for T cells is not perfect.
It was a carcinoma, not like sarcoma, like bone or like soft tissue.
So this has actually happened with a number of different cancers at this point. This one's 2015. So now a number of people who went on these checkpoint inhibitors for prostate cancer, diabetes. So it doesn't have to do with the cancer. And if there was a way to screen the patients, which maybe when you become independent scientists, students, postdocs, anything, when you go to the lab, maybe that will be something you can figure out, is a screen to keep these autoimmunities at bay. You good? Yeah.
Because this was so treatment induced, insulin would be great treatment for them, right? Because they wouldn't have any insulin resistance. Would the cells recover after treatment was stopped?
That with the
would the pancreas start to produce new cells?
No, what I understand is the pancreas done. Yeah. That and that was from talking to the doctor of somebody who's taking care of some prostate cancer patients. But they do have the option then of insulin. Mm-hmm. So balance, right? Which is better. Okay. So there's a lot of background. We know that a lot of different autoimmunities can follow immunotherapy. It's not just like taking water, unfortunately. So these are mainly from melanomas. You can get vitiligo, little white spots where your melanin is taken away. This is vitiligo in a mouse. And then think, where's another place that you have, besides your skin, another place that you have pigment in your uvea, right? And so this guy had to get, I guess they get steroids and they turn off all of the reactions, and most people it's fine, but other people it's not so good. And these are the lists of things, including death. So there's a number of things that can happen. And I like this slide because it is sort of a visual of what the T cells look like. So there's T cells in our blood that goes everywhere. We have all sorts of T cells. Some of them cross-react, some of them don't. Some of them are perfect for getting rid of pathogens, and some of them are perfect for getting rid of our pancreas in some people. And without the checkpoint inhibitors, they don't cross the line, right? They do what they're supposed to do. But when the checkpoint inhibitors come in, all of the T cells are being activated. It's not just the ones that are in the tumor, although since most of the immune response is happening in the tumor at the time, that's probably where most of the activity of the checkpoint is going to take place. And so some of those cells will cross the line, and some of them are going to be tumor specific. And I know you can't see this, but this little red cell is tumor specific, and these other cells are autoimmune specific. Okay, all right, I'm going to move on to the next immunotherapy, but this one is so mainly most checkpoints are targeting PD-1 and PD-L1. There's you saw the slide. There's a lot of different ones that are being tried. There are so many that are being tried, and they're being tried in combination. And so now you can have this conversation with your auntie when she wants to find out more about checkpoint inhibitors. Okay. So the next one I want to talk about are CAR T cell receptors. Okay. Have you heard about them? Okay. Everybody? Has anybody not heard about these? Okay, good. Okay, we're going to just talk about how they work. So, CAR T cells combine the best thing about antibodies and the best thing about T cells together. And so that's why they're chimeric, because they combine B cells and T cells. They're chimeric for a few reasons, but that's one of them. Okay, so the variable region from the antibody, remember the variable region, that's what the antibodies are designed to interact with. That's what they have high affinity for. So think about the specificity of these and combining it with the killing power of the T cells, right? And that's what CAR T cells look like. And so maybe I should do this in the other order. Okay, so this is how the CAR Ts work. Actually, I'm going to go back. I feel like this isn't the best slide all of a sudden. So we have the variable domains of the antibody, and that's combined with in a recombinant virus, that's combined with activation domains from a T cell receptor, which aren't shown here, but they stimulate the T cells to kill the targets. Okay, and I have a couple pictures of those, which will be in this slide. So this is the problem, right? We have leukemia, and it's got markers on it that are specific to leukemia, specific to B cells. So we have the tumor and the antigen, and this is the solution. So we have an antibody that we know is specific for the CD19. That's been tested, in fact. Have you heard of rituximab? So rituximab is an antibody that was used directly to get rid of CD19 expressing cells, and specifically leukemias and lymphomas. And so this T cell has been transduced with this molecule that has signals that activate the T cell to kill the leukemia cell. Bam. Okay. So how does this work in the clinic, or in the clinic and lab together? The T cells are collected out of the patient, and we need the patient's T cells because we talked about graft versus host. We don't want to have that happening with our cells of interest. So then we introduce the CAR T construct in a virus, and the virus then starts to make the construct, and it goes to the surface of the T cells, right? The T cells then get put back into the patient. This is an adoptive cell therapy, and then the patient is monitored. So what would you monitor in the patient? What?
Autoimmunity, like you saw with overactivation.
So you'd look for activation of the CARs, of the CAR expressing. Yeah, you'd look to see if you were getting rid of your leukemia. You would look to make sure that they weren't getting some sort of cytokine storm, which is actually pretty common. And specifically, okay, this is from one of the I got this from somebody who was taking care of the first patients that were treated with this. So one day before infusion, looking in the bone marrow, we have cells that express all sorts of CD19 and CD5, and those are not supposed to be in the bone marrow. Not like that. Not the only cells in the bone marrow, right? And all of the B cells are expressing one chain from the B cell, from the immunoglobulin, from the B cell receptor, or the antibody. It's got a lot of names. So there's usually about half and half there, right? So this person isn't doing very well. And then 1 month after infusion of the CAR Ts, you can see this big blob of CD19, CD5 positive cells has mostly gone away. And then if you just look at these cells, and you have to look very, very closely, there's some of each of them. Although it's probably nothing really in that. That would be how I would read that anyway. So, so that's good. These guys are on the road to recovery. Yes?
So if you're using a viral vector to introduce this CAR thing, how do you know that it's not going to integrate in a place that's just going to cause more cancer or other issues?
Yeah. So that's a really good question, and that we're actually now, Terry Fry, who is, are any of you in his lab? No. So Terry Fry, who is a CAR T cell aficionado here now, has just said at a talk that I recently heard that they're actually starting to worry about that now, because enough people have been infused with this therapy that sort of thing is starting to happen. And I think he talked about one patient. But putting something in there that will kill the CAR Ts, putting in a kill switch, is the solution to that. And we have that as a question coming up now.
What was the problem?
That possibly the virus could integrate someplace and cause other problems, yeah, or cause super activation, or cause some sort of unbalance, right? You could get a secondary cancer from the virus. So, okay, so these are expensive guys, right? So I saw this number in one place, and then in another place I saw $1.5 million, because in addition to actually getting the virus that's incorporated into your own T cells, and then you get this all put back in, you get antibodies to stop the cytokine storm, which are, $100,000 or something each, and you've got to stay in special rooms. So this isn't the cancer vaccine that was originally thought of at the beginning, that would be cheap and good for everybody. But just say you want to make this a little better. What would you want to add or delete to these CAR Ts? So you mentioned something, right? Maybe a kill switch would be one thing. What else? What turns a T cell off that we already learned about? PD-1. So maybe you could get rid of PD-1. What if you wanted to make a universal CAR? What would we have to get rid of? Maybe that if we wanted, so I have some extra T cells. I'm going to give them to you because of let's just say your friend has leukemia. So I'm gonna give your friend some leukemia cells, some CAR T cells. What else should we put in there? We have a kill switch. We have no PD-1. Maybe exactly. All of a sudden, we're gonna start getting some sort of graft versus host fight going in there. So let's get rid of the MHC. How about the endogenous T cell receptor? That hasn't been a problem yet, but since we're at it, let's just get rid of it. Okay. Oh, what do you know? There's that list. Yeah.
What kind of molecules have you found that can be like consistent between cancers that they can use it as universal treatment?
Right. So that's actually is really important. So what they have figured out, that universal antigen has been so far antigens like the CD19, which is expressed on B cells. So what happens to the endogenous B cells? You have your leukemia that you definitely get rid of, and those are gone. But what happens to the other B cells, like the ones that are going to help you get rid of your wintertime cold? Yeah, they're gone too. Yeah. Okay. So I don't know if we have very much time to talk about this, but one thing that I'm very interested in is trying to make antigen-specific T cell responses. So actually using the antigen that the T cell receptor was designed for, and trying to activate T cells with regards to that. And maybe you've seen this slide before, but the idea here is that certain cancers become more and more full of mutations that equals antigens, right? The immune surveillance hypothesis said that we should be able to use the T cells should recognize and delete tumors because of the antigens accumulated during the transformation process. And so some of these have a lot more antigens in them, and those are going to be the ones that are going to be possible to find more T cells in there. And those are actually the ones that work best by the checkpoint blockade therapies. These guys down here on the other end are mainly, a lot of these are found in kids, and they are not necessarily as mutated. So those are the ones that perhaps we have CAR therapies for. But what about the ones in the middle? And I think that we'll be able to figure out some things about antigens. And so we know that T cells can recognize antigens that have been dysregulated, like carcinoembryonic antigens, or cancer testes antigens, or some antigens that get overexpressed because of some developmental pathway. And so what we're working on in my lab is figuring out how can we develop good immune responses to self-antigens at the same, because then we can target more people, but at the same time trying to figure out how not to induce autoimmunity. So that's what I got. But the main things to remember are I guess I didn't write down what to remember, so I'll just tell you. The main things to think about in tumor immunology today are those checkpoint blockades therapies and the CAR T-cell therapies, and the things to look forward to in the future are more antigen-specific vaccines. Okay.